Have you ever looked at something seemingly simple, maybe like swirling milk into coffee, or perhaps something much bigger like clouds, and just thought, how does something so straightforward become so incredibly complex, so unpredictable?
Yeah, and what if that unpredictability isn't just, random noise? What if it's actually built into the system's basic rules?
That idea is fascinating, and it's exactly what we're diving into today. We're looking at a really foundational paper by Edward Lorenz.
Absolutely foundational. This work kind of cracked open the door to understanding complexity, not just in weather, but, well, all over the place.
So our mission here is to get you straight to the core ideas from this research. We'll be exploring things like nonlinearity, phase space, what deterministic chaos actually is.
And crucially, why it's so different from just randomness. That's a key point.
By the end, you should have a much clearer handle on this, well, this pretty mind-bending topic.
Okay, so let's start with the person, Edward Lorenz. Who was he?
Right. He was a researcher at MIT. His background was in meteorology and hydrodynamics.
So basically the science of how fluids flow, which includes the atmosphere, obviously. He was really focused on understanding these complex, often turbulent patterns in fluid flow.
Yeah, and you can really see that focus coming through right at the start of the paper in the introduction. He talks about flow patterns. Some are smooth, predictable, regular.
While others are irregular, messy, turbulent.
Exactly. And he points out the big challenge at the time. This turbulent behavior was a major hurdle for accurate short-range weather forecasting.
How do you predict the details when it seems so chaotic, so patternless on the surface?
So Lorenz had this really specific goal. Could he find or maybe build a mathematical system that was totally deterministic, following strict rules, no dice rolls involved?
But still produce that kind of non-periodic, turbulent-like behavior.
Yeah, he wanted to see if he could capture the essence of that atmospheric complexity in a more controlled mathematical setting.
Which brings us to the model system he used,
Yeah.
which was actually quite ingenious in its simplicity.
He used a really simplified set of equations, right? Just three differential equations.
That's it, three ordinary differential equations. They were derived from some earlier work by a guy named Saltzman on thermal convection.
Thermal convection, like warm air rising, cool air sinking, that kind of process.
Basically, yeah, boiled down to its mathematical bones. You have these three variables, usually called x, y, and z.
And the paper mentions they represent things like the intensity of that convection and maybe temperature differences driving it.
Exactly, things like that. It's a massive simplification of real weather, of course.
But that was the point, wasn't it? Strip away all the messy real-world details to see the fundamental dynamics underneath.
Precisely. And the absolute core reason why this simple system can act so complexly comes down to one critical property. The equations are nonlinear.
Nonlinearity. Okay, that's a term you hear constantly in complexity science. Can we break that down a bit? What does nonlinear mean for how a system behaves?
Well, the key thing is, if these equations were linear, the behavior would be, frankly, pretty boring.
Boring how? Like predictable?
Yeah, predictable. It would probably settle into a steady state, or maybe oscillate in a perfectly repeating cycle forever. Very simple.
Okay.
But because they're nonlinear, the relationships are more tangled. A change in one variable doesn't just add a proportional change elsewhere. It can get multiplied or interact in more complex ways.
So small causes don't always have small effects.
Exactly. And this paper really showed, maybe for one of the first times so clearly, that this nonlinearity, even in just three simple equations, could generate incredibly complex, non-repeating behavior.
Okay, so we've got this simple three-variable nonlinear system. How do you even visualize what it's doing? How do you track its behavior over time?
This is where the concept of phase space comes in.
Yeah.
It's super useful. Imagine an abstract space.
Okay.
Since our system has three variables, x, y, and z, we can think of this as a 3D space.
Okay.
At any single moment, the values of x, y, and z define one specific point in that space.
And that point represents the system's complete state right then.
Its entire state captured in a single point. Now, as the system changes over time following those nonlinear rules.
The point moves. It traces out a path in this phase space.
Exactly. That path is called the system's trajectory. And when Lorenz plotted these trajectories, you can see them in Figure 2 in the paper, the result is stunning.
What did it look like?
The trajectories loop around, kind of like orbiting two different centers, but they never settle down into a simple orbit. They never repeat the same path exactly.
But they won't just fly off to infinity either.
No, they stay within a certain bounded region. It's this incredibly complex, intricate dance within that space, kind of like a tangled skein of yarn.
Wow. Okay, so that visualization, tracking the path in phase space, leads directly to the paper's really big finding, right?
Yes, deterministic nonperiodic flow.
Let's unpack that. Deterministic means ruled by equations.
Completely. No randomness involved.
Yeah.
Its future is fully determined by its present.
But non-periodic means?
It never repeats. It never settles into a cycle. If you look at the graphs of X, Y, or Z over time, like in Figure 1, they just keep fluctuating irregularly. It looks chaotic.
So it looks unpredictable, even though it's following fixed rules. How does that work? If it's deterministic, shouldn't it be predictable?
This is the deepest insight. It relates to what Lorenz called the instability of this non-periodic flow. We now usually call it sensitive dependence on initial conditions.
Sensitive dependence.
Yep.
Okay, this is the butterfly effect idea.
That's the popular metaphor, yes.
Yeah.
What Lorenz showed is that this non-periodic behavior is incredibly sensitive to the starting point.
Meaning?
Meaning if you take two starting points in that phase space that are almost identical, like different by some tiny, tiny amount, maybe way beyond what you could even measure,
Okay.
their trajectories, their paths through phase space will start to diverge, and they diverge exponentially fast. Very quickly, they end up in completely different parts of that tangled shape.
Wow, so even the tiniest uncertainty about where you start
Gets blown up massively over time.
which makes long-term prediction practically impossible. Not because the rules are random, but because you can never know the starting state with perfect, infinite precision.
Exactly. Any microscopic error is amplified until the prediction is useless. That unpredictability arises from within the deterministic system itself.
Okay, this feels like the critical point. Let's really nail the difference between this deterministic chaos and actual randomness.
Right. They can look similar on the surface, both seem unpredictable, but the origin is completely different.
So, Lorenz's system, 100% deterministic, rules are fixed, no external chance involved.
Correct. Its behavior follows strictly from those nonlinear equations. True randomness, on the other hand, well, that implies there are no such underlying deterministic rules, or at least none that we can know or use. Think of, like, radioactive decay or truly random number generation.
There's no equation predicting the next event from the current state in the same way.
Precisely. So the aha moment from Lorenz is that you don't need external randomness to get unpredictable-looking behavior. Simple, deterministic, nonlinear rules can generate it internally through this sensitive dependence.
That's the core of deterministic chaos. Even if he didn't quite use that exact term in this paper, that's the phenomenon he uncovered.
Absolutely. And the implications were and are huge. This wasn't just some obscure mathematical curiosity about simplified weather.
How did it connect to the bigger picture?
Well, it suggested that any system with similar characteristics, nonlinear interactions, feedback loops, could potentially exhibit this kind of chaotic behavior.
So not just weather, like ecosystems, financial markets.
Potentially, yes.
Yeah.
Ecosystems, economies, fluid dynamics beyond weather, chemical reactions, even things like biological systems or social dynamics. Anywhere you have these kinds of complex nonlinear feedback loops, chaos might be lurking.
And the impact on our idea of prediction.
It was fundamental. It showed there are inherent limits to predictability in some systems. Not just because we lack data or computing power, but because the system itself has this sensitive dependence baked in. Unpredictability can be an intrinsic property.
That really changes things. It's not just about getting better measurements. Sometimes perfect long-term prediction is just off the table.
Exactly. It revealed a much deeper, more nuanced picture of how determinism and predictability relate, or rather, don't always relate.
Okay, so let's quickly recap the key takeaways from this deep dive. We started with Edward Lorenz, the MIT meteorologist, trying to understand turbulent flow.
We saw how he used a simplified mathematical model, just 3 nonlinear equations, to capture this complexity.
And that nonlinearity was absolutely key. It's what allowed simple rules to generate complex behavior, unlike linear systems.
We talked about phase space as a way to visualize the system state moving along a trajectory over time.
Which led to his major discovery, deterministic nonperiodic flow, a system following fixed rules that never repeats itself.
And the crucial insight explaining this: sensitive dependence on initial conditions. The butterfly effect. Tiny starting differences lead to vastly different outcomes.
Making long-term prediction impossible, even in a deterministic system. And we stress that this deterministic chaos is fundamentally different from true randomness, which lacks underlying rules.
Right. This unpredictability arises internally from the system's own dynamics.
This work really launched a whole new field, didn't it? A new way of looking at complex systems everywhere.
It absolutely did. It changed our understanding of predictability itself.
So maybe the final thought for you, the listener, to ponder is this. If a system as simple as Lorenz's three equations derived from basic physics can produce behavior so complex and sensitive that it defies long-term prediction,
What does that imply about the limits of predictability in the vastly more complex systems we encounter every day, in our own lives, in society, in the universe as a whole? How much apparent randomness out there might actually be underlying deterministic chaos?